Hello, everyone. In this session, we will be talking about simplifying capacity management using autoscaling. Just to help me out, just so that I can understand what the experience for autoscaling is in the room, if I can just get a quick show of hands, how many of you plan on using autoscaling for the very first time? And how many of you have been using autoscaling but are here to learn about the end-to-end capabilities and the new features that we've launched? And how many are here to hear Netflix as to how they are using autoscaling? Wow, OK. So it looks like we do have content that's going to satisfy pretty much all of you, so super excited. I'm always excited to be talking about this topic since there are a few dimensions to the elasticity that the AWS cloud provides. One of them is the ability to provision hundreds and thousands of servers in no time without any upfront capital expenditure. Another dimension is the one that we will be talking about in this session, that is around automating the provisioning and capacity management of your EC2 instances. Autoscaling is not just about adding or removing capacity as and when the traffic to your application changes, but there's a lot more to it than that. A number of our customers, they manage all their EC2 capacity using autoscaling, whether their application has one instance or 10 or even more. My name is Anup Kapoor. I'm the Senior Product Manager for the Autoscaling service, and I help our customers with maximizing their application performance while at the same time lowering the cost. I'm also super excited to have Netflix here with us, who will be sharing how they use autoscaling. Before we get started, I just wanted to quickly go over the three offerings that we have for autoscaling. The first one is EC2 autoscaling that we launched back in 2009, which helps with the capacity management of EC2 instances. The second one is application autoscaling, which we launched in 2016 when we started to extend the automatic provisioning of capacity to services beyond EC2. Today, we support 7 services. For compute, we support EC2 Container Service. For databases, Aurora and DynamoDB. For machine learning, SageMaker. We also support AppStream 2.0. The third is AWS autoscaling. This is something we launched earlier this year, which allows you to scale a number of services at the same time in a very simple fashion. So say, for example, you have an application that is using EC2 instances and DynamoDB tables. You can set up the automatic provisioning and scaling of all these resources from one single interface. But in this session, we will be doing a deep dive on EC2 autoscaling. This is not a trick question. The answer is E. Whenever I see an option which has all of the above, I always end up choosing that. So to begin with, I will be sharing with you how to get started with autoscaling and how to get the right software on your EC2 instances when you are using them with autoscaling. Second is, once you have the software installed on these instances, how can we work so that the effort required around maintaining these instances is minimized? And once we've done that, then we'll take a look at how to optimize the provisioning so that we can optimize for the availability and cost. But before we get started, I quickly want to go over what an autoscaling group or an ASG is, as this is a term that you will be hearing and using over and over again. An ASG is a logical group of instances. So for example, you have an application that is being powered by a number of EC2 instances. All those EC2 instances are going to be a part of a single ASG. It is bound by the minimum and maximum capacity. So the number of instances running in the ASG is not going to go beyond the maximum. So you don't have to worry about cost overruns or runaway scaling. And the same concept applies with the minimum capacity as well. Desired capacity is what determines the number of instances that should be running in the ASG at any given time. So the ASG is going to either launch instances or terminate instances so as to meet the desired capacity. Now, one of the questions is that when the instances come up, what are the properties of these instances going to be? So that's determined by the launch template. And this is something that you assign with the ASG when you configure or create one. So what is the instance type that's going to be launched, whether it's a C3 large, a C4 large, what are the Amazon machine image that's going to be associated with the instances that are launched. So all this data is contained in the launch template. With that, let's get to the first use case of automating the provisioning of these EC2 instances. So when the instances come up, they need to have the software and all the application code installed on them so that they can start accepting the traffic or start doing the work. One of the more popular ways that we've seen is using a golden image or a golden AMI, which has all the software and configuration already pre-baked into the AMI. And that's what you specify in the launch template that we saw before. So when the instance comes up, it already has all the code and application installed on it. The instance is ready to start accepting the traffic. The second is where you specify a base AMI, and then the instance is going to launch with the base AMI, and then you end up installing the code or the application as and when needed after the instance has launched. So one of the ways to achieve that is using the user data, which is in the launch template. So you can specify your scripts, and then as the instance launches, it's going to end up running the scripts and installing the code. ASG is also integrated with Code Deploy and Systems Manager. Also, if you're using one of the configuration management tools, such as Ansible, Puppet, Chef, you can use those as well. So as to pull or push the configuration as the instances come up. This is what a user data script looks like. So in this case, what I'm doing is, whenever the instance comes up, I want to install the system updates. I'm doing that using the yum update. And once that's done, I want to install the code deploy agent. So whenever the instance comes up, it already has the code deploy agent installed, ready to go, and the code deploy service can start interacting with the instances that just launched and can push the code as and when needed. Another use case which we see is that when the instance is coming up, you wanted to take additional actions, such as you want to attach an elastic IP address, you want to attach additional elastic network interfaces, or when the instance is terminating, you want to download the logs, or you want to persist the state of the instance. So this is what the life cycle of an instance in an ASG looks like. When the instance has to be added, first it goes into the pending state. Once all the work is done, then the second step is to go into the in-service state. So with lifecycle hooks, what you can do is you can pause the transition of the state from pending to in-service. And while it's paused, you can take the actions such as attaching an elastic IP address using automated Lambda functions. And similarly, even with the terminating state. So when it goes into the terminating state, you make it pause there, run your Lambda functions, download your logs, persist the state of the instance, and then move on to the terminated state. Instead of using lifecycle hooks, you can also choose to receive event notifications when these state transitions happen. So for example, when the instance launch is successful or termination is successful, we have full integration with Simple Notification Service and CloudWatch events. So say if you want to receive notifications and you want to send it to a pager alias whenever a launch is unsuccessful, you can do so, and then someone can manually check in. Or if you're using another system to do all the event logging, you can send all your events to that system and do your event logging. We also have full integration with Elastic Load Balancing with all three, the classic load balancer, the application load balancer, and the network load balancer. So all you've got to do is when you're setting up the ASG or creating the ASG, you specify the load balancer or the target crew, and then when the instance comes up, it is automatically going to end up getting registered behind the load balancer. So once we have the instance up and running and the ASG set up, we want to ensure that the work around maintaining this fleet is minimized. What that means is if anything were to happen to my instances, I want the remediation to happen automatically without any manual intervention. So we have integration with both EC2 health checks and ELB health checks. So say, for example, a very popular setup where the ASG is running behind a load balancer, and you have it configured so as to honor the ELB health checks. Say if the ELB health check fails, ASG is automatically going to end up launching a replacement instance. Now, from an AWS well-architected perspective, one of the best practices is that your EC2 capacity should be distributed across availability zones. So in this particular example, I have behind my ASG, I've selected 2 AZs, and the desired capacity is at this time 6 instances. So ASG is going to launch 3 instances in one AZ and the other 3 in the other AZ. So it's going to balance the capacity. And say if anything were to go wrong with one of the AZs, ASG is automatically going to end up retargeting the capacity to another AZ which is available. And once it does so, it's going to end up launching one instance. It's going to try and poke the AZ that was constrained, and as soon as that instance launch is successful, once again, it's going to end up rebalancing the capacity across the AZs that you have specified with your ASG. Now we've made it easier than ever to use spot instances with your ASGs so that you can get the benefit of spot instances, lower your cost by up to 90% with using spot instances. This is something we just launched 2 weeks ago. So earlier, your ASG was homogeneous. It could only have one instance type, and it could be only one pricing option. Now you can create an ASG which spans across pricing options, which are, for example, spot instances, on-demand, reserved instances, and you can span them across instance types. So before you had to create one ASG per instance type and one pricing option. Now, when you're creating an ASG, all you've got to do is specify how much of your capacity should be fulfilled with on-demand instances and how much of your capacity in percentage terms should be fulfilled with on-demand instances. And you also specify which instance types work for you. From there, ASG is going to automatically mix and match these combinations so as to provision capacity for you at the lowest price. If you have RIs for the instance types that you have specified, you will end up getting the RI benefit. We will be doing a deep dive on this topic later this afternoon in a chalk talk, and we will have a repeat for that this Thursday as well. The last use case I want to talk about is that I want to grow or shrink my capacity automatically as the load to my application changes. What that means is I do not want to provision for peak capacity at all times so as to ensure that the application behavior is going to be fine. So in other words, I don't want to be paying for capacity that I'm not using, and I do not want my application to have sluggish behavior if I don't have enough capacity. So this all goes back to the concept that we discussed earlier about the min, max, and the desired size of the ASG. So the question becomes is, how and when do each of these parameters need to change? The easiest way of achieving this is you simply go into the ASG and update one of these parameters. As soon as you enter them, the ASG is going to end up getting to the new state. If you have a known pattern, for example, a 9 to 5 pattern where you want to bring up the capacity in the morning at 9 a.m. and you want to bring it down at 5 p.m. in the afternoon, you can do so using scheduled scaling. If you have more complex patterns, you can do all that with scheduled scaling. The third is dynamic scaling with target tracking. Target tracking is something we launched last year. It's gained a lot of popularity. It works just like a thermostat or a cruise control in your car. All you've got to do is you want to pick the metric that you want to scale on. So for example, the average CPU utilization of the ASG. And you end up selecting the target that you want to maintain. So if you know that, yes, your application works just fine as long as the CPU utilization is below 50%, that's what you end up setting the target at. So in this example, we have traffic coming to the load balancer, which goes forward to the instances. And we see that the average CPU utilization is at 50%. As more traffic starts to come into the load balancer, more work has to be done by the instances, and the CPU utilization goes up. In this case, target tracking determines how many more instances does it need to launch so as to bring the CPU utilization back to the normal level. So in this case, it determines it needs another 5 instances. So as soon as target tracking is able to launch another 5 instances, the CPU utilization goes back to the normal level. And once again, everything is fine. You can also set up dynamic scaling with step scaling policies. While target tracking does all this work for you, if for any reason you want to have finer grain control of the steps and of the alarms that need to be defined, you can do so. You can configure the alarms manually. You can configure the thresholds associated with those alarms. And then you can set up the steps. So for example, you want to say, if the alarm is breached by at 50%, of CPU utilization, I want to add 2 instances. If it breaches 60%, I want to add 4 instances. If it breaches 70%, I want to add 6 instances. The same concept applies with scaling in or removing instances as well. The last is predictive scaling. This is something we launched just last week. There's another session going on at this time talking about this. So with target tracking, what we saw was target tracking adds or removes capacity in response to the changing load to your application. With predictive scaling, it uses machine learning and the models that we have been able to train with the billions of data points that we have from Amazon.com. And what it does is it looks at your historical traffic coming into your ASG, and then based on that, it predicts what the traffic in the future is going to be. At the same time, it also runs a regression model to understand how many instances need to be provisioned so as to cater the traffic that's going to be coming in based on the prediction. So target tracking and predictive scaling, they are complementary to each other, and they work extremely well when used in combination. With that, now I would love for Netflix to come up and share how Netflix operates at the scale at which they do using autoscaling.
Thank you, Anu. Speaking of the Netflix scale, we operate a global service. We have more than 137 million subscribers as of Q3. It's a little bit more now. One statistic that is not very often quoted, but I think is a very, very indicative of our scale, is the fact that we support over 1,700 device types, including TVs, mobile, tablets, set-top boxes, you name it. If it has a screen and HDMI out, likely it can run Netflix. We deploy in 3 AWS regions. We have over 250,000 reserved instances and over 20,000 ASGs across 3 regions. We operate a massive network of Open Connect appliances, over 10,000 boxes with exabyte-level storage. Our data warehouse size is over 100 petabytes. I think this estimate is a little bit on the conservative side, and we run hundreds of A/B tests a year. How do we support this scale? Well, with help of AWS autoscaling. It all starts with provisioning. And when it comes to provisioning, autoscaling gives us plenty of options. We can choose from instance bootstrapping options, we can choose from rebalancing options, health check options, so on and so forth. Also, autoscaling gives us a lot of APIs and integration points. We use Spinnaker. This is an open source software that was developed primarily by Netflix. We use it internally. We use it as a continuous delivery, and it's the next layer on the top of AWS provided features, on the top of AWS autoscaling. Spinnaker gives us abstractions for managing autoscaling groups. For example, Spinnaker has an atomic operation for cloning an ASG. We're talking about deep cloning with security groups, scaling policies, and so on and so forth. Based on these abstractions, based on these building blocks, Spinnaker allows us to create various automation and pipelines and to automate our deployment process. And lastly, Spinnaker integrates with a lot of other Netflix tools for telemetry, reporting, so on and so forth. On the top of Spinnaker, we built something that we called immutable infrastructure. We bootstrap our instances with pre-baked golden AMI. We never change the software on the instances. We never patch them during their lifetime. When we need to deploy a new version of the code, we use red-black deploys. The industry standard name for this is blue-green, but I'll stick with Netflix nomenclature. That's what we call it internally, red-black deploys. Basically, it refers to the pattern of spinning up a new ASG with a new AMI that has a new version of the code, then shifting the traffic over to that new ASG, and then destroying the old ASG. And lastly, in each region, we deploy across 3 availability zones, and we rely on autoscaling to balance us evenly across AZs. Replacing unhealthy instances or fleet management. This refers to the feature of autoscaling that guarantees that autoscaling will maintain desired capacity and replace instances that either failed health check or were terminated externally or otherwise disappears. A few years ago, we developed Chaos Monkey. Some of you might be familiar with this tool. Maybe some of you run it in your environment as well. The premise is simple. Chaos Monkey terminates instances at random with a certain frequency, of course. We did it to ensure that our software is resilient to failures. We did it to ensure that the loss of any single instance doesn't affect our service. We refer to it as a continuous resiliency testing. But this tool was made possible by the fact that autoscaling replaces those instances that Chaos Monkey terminates and allows our service to move on. A more pragmatic approach, alerting. We have a system that supports both threshold-based alerts and outlier detection alerts. When we detect that a particular instance have a higher error rate, higher CPU utilization, or any other conditions that might be adverse to the service overall, we can choose to terminate that instance, and AWS replaces it with a brand new, healthy instance. Lifecycle hooks. Lifecycle hooks allow you to get notifications and to run your own commands or code based on the life cycle of the instance when it transitions from pending to in service to terminating to finally terminated. At Netflix, we use something that we call a discovery service. You can think of it as an application level DNS. Every instance, when it comes up, it registers in the application discovery service, and it becomes discoverable by any other instances. It's exactly the premise of the DNS. So when we terminate an instance, or when it gets terminated by dynamic scaling, the instance deregisters from discovery. The problem is, discovery has a propagation delay. And sometimes the propagation delay could be longer than the time it takes for the instance to terminate. What it results in is that some instances within that region might attempt to send traffic to the instance that was terminated already. Well, that obviously leads to errors. How do we deal with this problem? With lifecycle hooks, we have a lifecycle hook on termination. We send the deregister event to discovery when the lifecycle hook just kicks in, and then we wait. We quiesce the instance, we drain all the traffic, we make sure that the state is propagated throughout the entire region, and then we proceed with terminations. Dynamic scaling. So about 3 slides ago, I said that Netflix have over 250,000 of reserved instances. So you might be asking, well, why do you even need dynamic scaling, right? Provision everything for peak. That's it, done. Okay, let me make a case for dynamic scaling. Take a look at these 2 images. They look identical. Even though if you look at it pixel by pixel, you'll see differences. These are still frames from one of our originals, Altered Carbon. The difference between these 2 images is that one of them was captured from a stream at 790 kilobit per second, while the other image, the image on the right, was captured from a stream encoded at 383 kilobit per second. That's less than a half of their original bitrate. Netflix employs something that we call encoding optimization to compress our streams without a perceived loss in quality. Video encoding itself requires a lot of compute power and a lot of capacity, and running encoding optimization requires even more capacity. Where does it come from? Let's take a look. The bottom graph, the blue area, represents our capacity usage for a particular region for a particular instance type. You can clearly see the daily pattern here. At 7 p.m., a lot of people watching Netflix, a lot of people streaming. At 3 a.m., not so much. Well, still surprisingly, a lot of people, but not as much as at 7 p.m. So we don't need as much capacity to support streaming at 3 a.m. as we need at our peak at 7 p.m. So we scale up and down, and that unused capacity can be used for encoding. And the graph on the top, the yellow area on the top, represents the capacity that we used for encoding job. We built a pipeline that harvests the capacity that is unused during our off-peak hours and uses it for encoding. Other benefits and usages of dynamic scaling, recommendations. Our catalog is always expanding, our subscriber base is always expanding, and we need better recommendations. Better recommendations a lot of times require more sophisticated algorithms, and they require more capacity to implement. The bulk of recommendations, we're running it during off-peak hours as well, reusing the same capacity that we normally use for streaming. Red-black deploys. How does autoscaling play into that? Well, imagine if we provision it statically for peak. When we do a red-black deploy, we have to clone the ASG. We have to double up the capacity. If we were statically provisioned, we would have to double up our peak capacity. We usually do deploys in the morning hours when our ASG is maybe at the half size or maybe even less than that. That allows us to save capacity on red-black deploys. This is an interesting use case. Regional failover, internal code name Kong, hence the picture of a Kong. Netflix deploys in 3 regions, and we developed a system that can evacuate any single region, and we can still serve traffic from the remaining 2 AWS regions. How does autoscaling help with that? Well, if you think about, for example, North Virginia versus Ireland, we see the same daily patterns of peaks and troughs in each region. But the peaks are shifted roughly 7-8 hours. So when there is a peak in North Virginia, there's plenty of spare capacity in Ireland. So when we're shifting traffic, we don't have to provision Ireland for the peak of peaks. We have to provision it much less than that. You can think of it as adding 2 sine waves that are shifted in time. When you're adding them, the local peak is not doubling up, it's much less. Let's talk about dynamic scaling, what it is, and how to set it up. In a nutshell, dynamic scaling is a feedback loop. It's a system with a feedback loop. Managed ASG sends metrics to CloudWatch. CloudWatch sends a notification when the metric breaches a threshold, and scaling policy receives a notification and acts upon it, either adding or removing capacity. And feedback loop is thus complete, and then it repeats. Each of these components have a few tunables. Well, obviously, the most important one is probably the metric and the threshold. There is a number of other tunables. We'll go through it later in the presentation. There is also 3 fundamental properties of dynamic scaling that I wanted you to be aware of. First is a delayed reaction. As any system with a feedback loop, autoscaling, dynamic scaling inherently has a certain lag associated with it. It's not good, it's not bad, it's a fact. Again, any system with a feedback loop has it. And going back to what Anoop said, one of the ways it could be addressed is with introduction of predictive scaling. We don't use it at Netflix, not yet. It was released only last week, but it sounds very promising in the sense that it could address the delayed reaction, in addition to what target tracking already does. Another property is that autoscaling, dynamic scaling, is comprised of multiple policies. You set them up individually, they act individually, but the result, the end result, is a combined result of multiple policies acting together. And lastly, dynamic scaling is always bound by min and max ASG size. It only ever changes desired size. It never ever changes min or max size. So let's see how we go about setting up dynamic scaling. First, we need to pick the metric. Then we need to set the target or our scaling threshold. After that is done, we usually look at our traffic patterns and see if we need to adjust our targets or any parameters of our scaling based on our traffic patterns. And lastly, once we get everything, we set up policies. Let's go through this step by step in more details. What metric? This is such a popular question that I even made an XKCD style comic about it. The guy on the right is me, the guy on the left is a service owner that comes to me and asks, which metric should I scale on? The answer is usually, you should scale on something that shows how busy your instance is, at something that changes proportionately to the number of instances in the ASG. Well, this answer probably is not good enough because a lot of times service owners tell me how important the service is, what it does, what frameworks it uses, and business use case, and repeat the question. So now that you know all of this, can you please tell me what to scale on? Okay, to explain it, I prepared this slide. Generally, metrics fall under two categories. It's throughput-like metrics and resource utilization-like metrics. It's very easy to relate to this. That's how humans assess the work that we do as well. You can think of it in terms of how many miles I run or how many widgets I make, and that would be the throughput. Or you can think of it in terms of how tired I am and use, for example, a heart rate as a proxy of that, and that would be resource utilization. AWS provides a few metrics that fall under these categories. Request count per target is a metric published by ALB that shows the number of instances the number of requests that each instance processes. And average CPU utilization is a metric that is published by ASG that shows average CPU utilization per ASG. There's pros and cons in this approach, as both of them are suitable for setting up dynamic scaling. I really, really like throughput because it's very intuitive. It's very easy to do math on it. If you have an estimate of how much traffic you're going to get, and if you know your threshold, your target, you can divide one by another and get an estimate of how much capacity you would need to hold this traffic. The downside of throughput is it tends to drift over time as we develop and deploy new features, as we introduce different request types, and the mix between request type changes. It's somewhat of a moving target. CPU utilization, on the other hand, doesn't have these problems. We can set CPU utilization. We can normalize our workload at a set CPU utilization. If, let's say, you want to scale at 50% CPU utilization, and if you deploy a new version of code that has heavier requests, that has new features, that consume more CPU, the ASG would simply scale up accordingly to accommodate to keep you at the same CPU level. Autoscaling on multiple metrics is something that AWS supports, and sometimes it might be tempting to do. However, in our experience, we found that setting up dynamic scaling on multiple metrics makes it a little bit harder to reason about scaling behavior. It's also easier to get in a situation when different metrics point in a different directions and make autoscaling oscillate, scale up and down repeatedly. At Netflix, our common setup, our typical Netflix setup, involves scaling up and down on throughput. We also have emergency scale-up policy on CPU. We call it the hammer rule. For example, if we have an influx of requests, we can drop the hammer, scale up by 50 or 100%, and survive this sudden surge in requests. Another option is to scale straight on CPU, and especially with target tracking, this option works really, really well. What is my target? That is probably the most influential decision you will make when setting up autoscaling. There's plenty of tools that can generate synthetic load to load test your service. You can see some of these tools on the screen. Well, I know curl is not a load testing tool, but I've seen it being used as such, and why not? If you have to generate 5 requests per second, it works. There's also plenty of free and commercial tools that can capture the traffic in your production environment and replace it in your staging or test environment. All these solutions come with certain disadvantages. When you're talking about replaying the traffic, you have to synchronize your prod and test environments. At Netflix scale, it becomes a nightmare. It quickly grows out of hand. So what is our answer to this? Our answer is squeeze testing. Squeeze testing is a Netflix term that refers to load testing with live production traffic. How do we do this? Here's how. Here's an example of mid-tier services. The service on the right serves traffic to a bunch of clients on the left. This is a normal flow of traffic. What we do is we clone the server ASG with the same AMI, and we create a separate ASG with the same AMI with a single instance in it. That would be our system under squeeze. Then we create an instance of proxy that would help us to manage our traffic, to divert the traffic. Then we divert a portion of the traffic from our clients to proxy then proxy measures a controlled throughput and sends it to the system under squeeze, and the excess of traffic goes back to the server ASG. This is live traffic. We don't lose any single request. It goes either to system under squeeze or it goes back to the server ASG. Ultimately, by turning this knob, the controlled throughput, we can see how our service behaves under load. The good thing about this approach is that we're not squeezing the entire ASG. We're only squeezing a single instance. So that minimizes the blast radius, and that also allows us to see how the service fails. We have other mechanisms in place, such as retries, to deal with failures, and we feel confident that the information we get out of these experiments is worth it. Speaking of failures, I think it's extremely important to understand the failures. I know nobody likes to think about it, nobody likes to talk about it, but as a performance and reliability engineer, I have to deal with failures quite often. Here is an example. The service on the left exhibits normal pattern, normal behavior. The throughput doubles up from roughly 90 to 180 requests per second. CPU roughly doubles up from 40 to 80%. Latency almost doubles up, less than that, from 30 to 50 milliseconds. But this service keeps going. It keeps servicing requests. The service on the right exhibits a very, very different pattern. At some point, when RPS, when our throughput reaches a certain threshold, this service simply breaks down. The CPU goes from 40 to over 80%, close to 100% utilization. Latency jumps from milliseconds to over a second, and throughput drops. This service fails. Here, this illustrates these two patterns. The service on the left keeps going. The service on the right fails. How is it related to auto-scaling? Here's how. If you operate a service on the left, the good service, then it's a business decision. It's a trade-off. You have a choice. If you have an SLA for latency, run the service cooler, pay a little bit more for the capacity, and meet the SLA. If you don't have the SLA and you're perfectly fine with running it at 60 millisecond response time as opposed to 30 millisecond, then you can run the service a little bit hotter and save on capacity. When you operate a service on the right, you don't have this luxury, you don't have this choice. You have to make sure that your scaling target is way below that point at which this service breaks. Speaking of traffic patterns, this is a traffic pattern for our typical mid-tier service comparing Friday morning versus Saturday morning. Usually when people talk about auto-scaling, the question is, will auto-scaling give me enough instances to sustain my traffic at peak? And usually my answer is yes, do not worry about your peak. Auto-scaling will give you instances up to your max size. The peak is not a problem. We found out that the morning hours are more dangerous from auto-scaling perspective than the peak hours. Here's why. Usually the ASGs at the lowest size, we have less instances to deal with the incoming traffic, and the rapid increase in incoming traffic can make it hard for auto-scaling to keep up. Another pattern, another anti-pattern, I should say, is mixing interactive and batch traffic. In this example, you can see that the batch service came in and started sending roughly 30% of the overall traffic to this particular ASG. That's a lot. And this traffic ramped up in virtually no time, in a couple of minutes. And that could put a lot of strain on auto-scaling. Auto-scaling might not be able to keep up with that. So The way I think about it is that rate of change of your metric, of your throughput, of your whatever metric you're monitoring, is more important than the peak volume. You can think of it as velocity versus acceleration. A constant velocity, no matter how high it is, do you no harm. However, a high acceleration can do some damage. All right, at this point, we have our metric, we have our target, we understand the traffic patterns, and now it's time to set up scaling policies. These graphs represent a service that scales on throughput. The graph on the top shows the capacity, the ASG size, that's the gray area, versus the incoming traffic, that's the pink line. You can see that the shapes of ASG size and incoming traffic are roughly the same. As traffic goes up and down, ASG scales up and down to accommodate this traffic. The bottom graph, however, is more telling, and it shows the essence of how dynamic scaling works. It shows per instance throughput. This is the metric we scale on, average throughput per instance. And you can see that we bind the throughput, we create this, the band between scale up and scale down threshold. When the metric goes above scale up threshold, ASG adds capacity. And you can see as our traffic ramps up, the metric keeps bumping up against the scale up threshold, against the ceiling, and ASG keeps adding capacity. On the way down, when the traffic dwindles, it keeps bumping against the floor, against our scale down threshold, and ASG keeps removing capacity. Also, some people prefer to think about this band as a dead zone. That is because for as long as the metric is within that band, ASG takes no action. If you're below your scale up threshold and above your scale down threshold, it's a no action. Well, sounds simple. Let's see what could go wrong with that. This is an example of no-rush scaling. I have a couple of these examples, and each of them come with a little story. In this particular case, you can see that ASG scales too slowly. It doesn't follow the incoming traffic. It's much slower than that. You can see that that average throughput per instance goes way below scale down threshold, which means we're wasting capacity, and it goes above the scale up threshold sometimes, which means that these instances runs dangerously hot. So the story is instead of setting the scaling amount in terms of percentage of ASG, the team used the number of instances. So this ASG has a size roughly between 300 and 400 instances. So 5% versus 5 instances makes difference in this case. The remedy was to increase scaling amounts or migrate to target tracking. Target tracking doesn't have this problem. Another example, Twitchy scaling, quite the opposite. In this particular case, the service owners wasn't sure what is a good scaling amount, so they decided to scale up by 100% every time. Essentially, when the average throughput reaches the scale up threshold, ASG doubles up. That's why you see the spikes. But what happens is, as soon as it doubles up, the average throughput drops below the scale down threshold, and ASG immediately starts scaling down. This leads to unnecessary capacity churn. And again, in this case, target tracking would have prevented it from happening. Target tracking manages everything automatically. Last example, actually my favorite example, should I stay or should I go? Here's the story behind this example. One of the teams discovered a performance regression on their service. They discovered this on Friday afternoon, so basically they have a choice, either to push a fix going into the weekend or scale up and survive the weekend and deal with it on Monday. Generally, we do not endorse deploying code changes on Friday going into the weekend. That is just a safe reliability practice. So the team followed this practice. They chose not to deploy the fix. They chose to scale their service up. How do you do this? Well, you can scale your service up by reducing your scale-up threshold. Reducing your scale-up threshold makes sure that ASG starts scaling up sooner. And that's what they did. But if you think about it, when they reduced their scale-up threshold, they got rid of the band. They used to have the band. Then they reduced their scale-up threshold. Now scale-up and scale-down are at the same value. There is no more band. There is no more dead zone. The auto-scaling cannot stabilize. And that is why you see that average throughput keeps oscillating. And in the top graph, you see that ASG size keeps oscillating as well. That's what happens when you remove this band. Well, again, you guessed it, target tracking has none of these problems. If the service used target tracking, they wouldn't have this problem. But if you use step scaling, make sure that you have this band and it's wide enough to avoid oscillations. Target tracking, as Anoop mentioned, it's a thermostat, and this is a perfect analogy. You can set the thermostat and let it do the rest. But if you're using step policies, you can also think of it as a step policy with automatic unlimited steps. Target tracking has all the benefits of step scaling without the complexity of setting up each individual step. In addition to that, target tracking gives you sensitivity to the rate of change. When the traffic is changing slowly, target tracking gives you less capacity and saves cost. When the traffic is changing rapidly, target tracking gives you more capacity and saves you from trouble. Easy setup, in my personal opinion, easy setup alone is worth for migrating to target tracking, for considering target tracking. You've seen the examples. You've seen how autoscaling could be misconfigured. Target tracking takes care of it. But in addition to that, target tracking also has a better adaptability to incoming traffic, and it learns over time. And all these features help to reduce cost and increase availability. It's not a zero-sum game. Innovations like target tracking can address both. And lastly, whether you have 25 or 250,000 instances, autoscaling has features for everyone. Netflix uses autoscaling extensively. It helps us to focus on our business needs and think less about infrastructure. Thank you.
Thank you so much, Vadim, for sharing all your experience at Netflix. And with that, I'd like to say that if you haven't been using autoscaling, I would definitely encourage you to create an ASG and start getting the benefit of automatic provisioning. If you've already been doing that, definitely start using dynamic scaling using target tracking. And if you've already been doing that as well, then definitely take a look at the new features that we've launched, get the benefits of spot instances, save up to 90%, and use predictive scaling. Thank you so much for your time. And we will be around if you have any questions. Would love to talk to you. And if you don't mind, just take a couple of minutes to enter the session survey. You know that we do these sessions for you, for our customers, so the feedback is really helpful for us to improve on. Thank you.
Thank you.